The inverse of a matrix. Finding the inverse of a matrix. First, it's important to understand that not all matrices have inverses. Invertible matrices are called non-singular and must be square matrices. So if it's not a square matrix, it doesn't have an inverse. But not all square matrices are invertible. If it's not invertible, it's called singular or non-invertible. So one way to find the inverse of a 2 by 2 matrix is using this equation. Now I'm going to show you several ways to find the inverse of a 2 by 2, of a 3 by 3, and so forth. And in this case, we're just going to practice using this equation. We're going to take 1 divided by the product of A times D minus B times C, which means you're going to be multiplying the diagonals. So let's find A inverse. And we can see that this is 1 divided by 6 minus 3. And we're going to multiply that. And I want you to notice the original matrix was A, B, C, D. Notice that this diagonal, the two values switched places. And this diagonal, the signs changed. So from my original matrix, I'm going to switch the 2 and the 3 to 3 and 2. I'm going to make this -1 and -3. So I'm going to go ahead and replace 6 minus 3 with 3. So I'm taking 1/3 times 3, and that gives me 1. 1/3 times -1, so -1/3. 1/3 times -3, so -1. And 1/3 times 2, so 2/3. Let's do a practice for the second question. And again, just good practice. It's still square, so it's possible it has an inverse. We're going to take that A inverse is equal to 1 divided by 9 minus 9. So I'm not even going to continue writing anything because what do I have? I have 1 divided by 0. So this is the perfect example where this is not invertible, or it is a singular matrix. What exactly is an inverse? What is it used for? Well, if we have an n by n, again, this is showing that this is a square matrix, is invertible when there exists another n by n matrix such that when we multiply them, we get the identity matrix. So if you'll recall, the identity matrix we just learned in our last section is a square matrix with ones along the diagonal. So in this particular case, because these are 2 by 2 matrices, we should end up with 1, 0, 0, 1 when I multiply A times B, if they are in fact inverses of one another. So let's take a look. A times B, I'm going to take 1, 4 and multiply. -3 plus 4 is 1. -4 plus 4 is 0. Now take the next row, -1, -3, and I get positive 3 plus -3, which is 0, and positive 4 plus -3, which is positive 1. Now let's go in reverse. BA. I should also get the identity matrix. So -3, -4. I get -3 plus 4, which is 1. I get -12 plus positive 12, which is 0. Take the next row, 1, 1. And I get 1 plus -1, which is 0. And 4 plus -3, which is 1. So we can see that whether we took A times B or B times A, I still get the identity matrix of, in this case, order 2. In our last example, we verified that if we multiplied A times B, we did get the identity matrix. And in the example before that, we talked about a way to find the inverse of a matrix. But what if we don't have a 2 by 2 matrix, or we don't want to use that inverse matrix formula? So we're going to start with a 2 by 2 just because the process is easier on a 2 by 2 matrix. But what we can do And again, I'm going to start with matrix A, and I'm going to find the inverse. Now, we already know the inverse is B, but we're going to arrive at that using Gauss-Jordan elimination. And here's how it works. We're going to take A, 1, 4, -1, -3. And I like to put a line here. Your book doesn't show that, but that's okay. And then on the right-hand side, I'm going to put the identity matrix. So because this is a 2 by 2, that would be 1, 0, 0, 1. And what I want to do is I want to use row operations to basically make the left-hand side 1, 0, 0, 1 and see what I get on the right. So let's take a look at that. If I wanted to get 1, I already have 1. So I'm not going to do anything to get 1 there, but I'm going to go ahead and take row 1 plus row 2 to be my new row 2. Now, be careful, because when I do that, I'm doing that for the entire row of 4 elements, so the whole thing. So the first row is remaining the same for now. Oops, 1, 0. And the second row, I'm taking 1 plus -1 to get 0, 4 plus -3 to get 1, 1 plus 0 to get 1, and 0 plus 1 to get 1. Now I have 1, 0. I want this element to be a 0. So how am I going to do that? I'm going to take -4 times row 2 and add it to row 1 to be my new row 1. That's going to give me my same row 2. And in row 1, I'm going to take -4 times each of these elements and add it to row 1. So that gives me 0 plus 1, which is 1, -4 plus 4, which is 0, -4 plus 1, which is -3, and -4 plus 0, which is -4. Now, once you've done all of the row operations and you have arrived at where the left-hand side is the identity matrix, the right-hand side is your inverse matrix. Now, I want you to notice that it's the same matrix, matrix B, that we already knew was the inverse. So why do I bring this up when we already have a very easy way to find the inverse matrix for a 2 by 2? Because in a 3 by 3 matrix, we don't have a handy little equation. We have to use Gauss-Jordan for now. Now we're going to find the inverse of a 3 by 3 matrix. Now keep in mind that yes, I'm aware there are multiple different ways of using technology to determine the inverse, but just in case you have to find it by hand, here's how we would do it. We would start with the original matrix, 1, 0, -1, -6, 2, 3, and on the right we would have the identity matrix. Now I'm going to do row operations until the left-hand side looks like the identity matrix. So to begin, and I'm going to try to do more than one step at a time, so I'm going to show my row operations, but I'm going to take row -1 plus row 2 to be my new row 2. And at the same time, so I'm kind of cheating, but I don't want to make a really super long video, I'm going to take 6 times row 1 plus row 3 to be my new row 3. So I'm going to change 2 rows at the same time, but notice row 2 and 3 are separate. We're not using them to affect the other row. So row 1's not changing. Row 2 is negative row 1 plus row 2, so I'm taking a negative times the first row, so that's -1 plus 1 is 0, positive 1 plus 1 plus 0 is 1, 0 plus -1 is -1, -1 plus 0, 0 plus 1, 0 plus 0, and also now I'm going to take 6 times the first row and add it to the last row, so 6 plus -6 is 0, -6 plus 2, 0 plus 3, 6 plus 0, 0 plus 0, 0 plus 1. Just trying to cut down the amount of writing and work that we're showing. Next, I'm going to get rid of this 4, so I'm going to take 4, row 2 plus row 3 to be my new row 3. That's going to give me a same row 1, so nothing has happened here. Row 2, nothing has happened. And in row 3, I'm going to take 4 times row 2. So 4 times 0 is 0 plus 0. 4 plus negative 4 is 0. Negative 4 plus 3, negative 1. Negative 4 plus 6, 4 plus 0, and 0 plus 1. So again, looking good on the left-hand side, but this needs to be a positive 1. So I'm just going to take negative row 3 to be my new row 3. That's going to give me 1, negative 1, 0, 1, 0, 0, 0, 1, negative 1, negative 1, 1, 0, and then just negating everything in this last row. Negative 2, negative 4, negative 1. So what I have now is row echelon form, and I need it to be reduced row echelon form. So that means I'm going to start right here getting rid of that negative 1. So I'm going to take row 3 plus row 2 to be my new row 2. So row 1 always gets saved for last. Row 3, nothing's happening to you this time around. And row 2, we're adding row 3. So 0 plus 0 is 0. 1 plus 0 is 1. Negative 1 plus 1 is 0. That's what we wanted. Negative 1 plus negative 2 is negative 3. 1 plus negative 4 is negative 3. 0 plus negative 1 is negative 1. So we're almost done. I'm going to move this guy over because he looks kind of funny. Finally, I have to get rid of this negative 1, so I'm going to take row 2 plus row 1 to be my new row 1, and then I should have my inverse. So this row stays the same. Second row stays the same. And first row is row 2 plus row 1. So 1 plus 0 is 1. Negative 1 plus 1 is 0. 0 plus 0 is 0. 1 plus negative 3, negative 2. Negative 3, negative 1. So what is the inverse? A inverse should be negative 2, negative 3, negative 1. Negative 3, negative 3, negative 1, negative 2, negative 4, negative 1. Now, before we finish this slide, I do want to point out that I have purposely chosen some nice examples where, if you'll notice, everything is happy. We have whole numbers, integers, we don't have fractions, decimals, and so forth. That's not always the case, so I certainly encourage you, whenever you have a question like this, to use technology to check your work, but just don't be concerned if you end up with fractions or decimals. I've already shown you how to use Desmos matrix. There is an inverse option, so I could go to Desmos matrix, plug this guy in, and find the inverse, and would find this without breaking a sweat. Since I've just talked about it, let's go ahead and use desmos.com/matrix to verify that we found the inverse correctly previously. So I'm just going to go to A equals new matrix and make it 3 by 3. I'm going to enter in my original matrix, and then I'm going to let Desmos do its magic. So I'm going to do A inverse, and notice we have the exact same values that we found by hand. Properties of inverses. Let's take a look now at properties of inverses. The first property says that if you have an invertible matrix and you take the inverse and then you take the inverse of the inverse, you end up back where you started, essentially saying inverses will undo one another. If you have a to the kth power and you take the inverse, it's the same as taking a inverse and then to the kth power. We're going to verify that one together. C, which is a scalar, so if you have a scalar times a matrix and then take the inverse of that, it's the same as taking 1 divided by C times the inverse of the matrix. Now that one's the trickiest one, but if you think about multiplication and the inverse of, say, what's the multiplicative inverse of 5? The multiplicative inverse of 5 would be 1/5, because 5 times 1/5 arrives me back to 1, which is the multiplicative identity. So it makes sense that if I had a scalar, that if I'm multiplying it by a first and then taking the inverse, it's the same as taking the inverse matrix multiplied by the inverse, multiplicative inverse of C. And finally, we have A transpose inverse is the same as A inverse transpose. Now, you can use Desmos to verify any of those. We're going to show that A to the -2, 2 different ways, is the same solution. So I'm going to take A squared and then to the inverse, or A inverse, A inverse and then squared, and I get the exact same solution. Let's take a look at the inverse of a product. So if A and B are, again, invertible matrices of order n, again, they're square, then AB is invertible. And if you take AB and find the inverse, it's the same as taking B inverse times A inverse. So this is very important. I want you to notice that the order has changed. We already talked about matrix multiplication not being commutative. You can't just switch the order, but when you are taking the inverse, you have to take the inverse of the opposite order. So let's verify with A and B. Again, I'm going to take AB inverse, and I'm going to show that it's the same as B inverse times A inverse. And I'm going to show that it's not the same as A inverse times B inverse. We can see that it's not the same, but these two are the same, which verifies that property. Finally, I want to look at the cancellation properties, and these are super duper important. We're saying that if C is invertible, then the properties below are true. If AC is equal to BC, then A is equal to B. Now, what they don't show in this property is that they're saying AC is equal to BC, then if I take it times C inverse on the right, which is why it's called right cancellation, C inverse is the identity. So essentially that goes away and leaves me with A equals B, which is what they're telling me. If CA equals CB, so just as before, CA equals CB, they're saying you must multiply on the left side by C inverse. C inverse times C is the identity and goes away, and therefore I have A equals B. Now, why am I making a big deal out of it? Because we talked in lesson 2.1 about the matrix equation. And I said, guess what? Later on, you're going to learn how to take A inverse times A, X is equal to A inverse times B, and therefore end up with X is equal to A inverse B. Well, that time is now, my friend. We are going to learn about the matrix equation. Solving a system of equations using the inverse. We just reminded ourselves that if we have the matrix equation, which is AX is equal to B, if I multiply by A inverse on the left-hand side of each side of my equation, then A and A inverse turn into the identity and essentially go away, leaving me with X is equal to A inverse B. Now, why is this important? Because I can take this system and notice that in each of these systems, the left-hand side is the same. So we're just going to get a little extra practice by changing the B column. But essentially what we're saying is let's rewrite this as 2, 3, 1, 3, 3, 1, 2, 4, 1 times x, which is x, y, z, or if it was written as x1, y1, x1, x2, x3, same thing, basically our unknowns, is equal to b. So for my first equation, that's -1, 1, -2, that if I'm able to take a and find the inverse, then I can solve for x, y, and z by taking A inverse, which is going to be a 3 by 3 matrix, and multiplying it by B, which is in this case -1, 1, -2, but could also be 4, 8, 5 or 0, 0, 0, and that's going to find my solution for me. Now, we've already done in this video, the first parts of this video, a lot of math. So we've done all of the work by hand. So for the sake of time in this video, I'm just going to use Desmos to find the inverse. But if you needed to, remember, how do we find the inverse of this matrix? You would use the identity matrix on the right-hand side. You would use Gauss-Jordan elimination to turn the left-hand side into the identity matrix. And do all of the row operations, which takes quite a while, which is why we're not going to do it since this video is already kind of lengthy. So I already have A inputted. I'm going to find A inverse, and that is my matrix, inverse matrix that I'm going to now use to solve the system of equations, all three of the systems. Now, we did cheat a little bit on that last one to find the inverse matrix, and that is where this came from. So this is A inverse, and notice it's the same for all three examples. And we could certainly cheat again and use Desmos to take A inverse times each of these B matrices. Again, these are just column matrices or vectors. So, but let's go ahead and do it by hand. This is going to give us our solution. So remember, this is x, y, and z. And our result is going to be the results for x, y, and z. So I'm going to take -1, 1, 0 to get 1 plus 1 plus 0, that's 2. To get, erasing that, to get -1, 0, 1 gives me 1 plus 0 plus -2. So 1 plus -2 is -1. And then finally 6, -2, -3 gives me -6 plus -2, which is -8, plus 6, which is -2. So here's my solution to the first system of equations. And that was when the B vector was -1, 1, -2. Now I can do the same thing for the others. So again, this is going to be x, y, and z, which typically would be over here. X, y, z is equal to, I just forgot to put that on the slide. So now I'm going to do -1 times 4. Let's go ahead and rewrite it. -1, 1, 0. So -1 times 4 is -4, plus 1 plus 0 is -3. Next row, turn the row into a column. -1, 0, 1 gives me -4 plus 0 plus -7 or -11. And finally, 6, -2, -3 gives me 24 plus -2, which is 22, plus 21. So 22 plus 21 is 43. And then we have our last example. So our last example, again, x, y, z. And I can see that this is going to be, because I'm multiplying by the 0 vector, is going to be 0, 0, 0, which is going to be the trivial solution. So remember, this is a homogeneous system and always has that trivial solution of 0, 0, 0. Up next, section 2.4, elementary matrices.